Hey everyone, here with the short video that I told you about that covers the rest of the chi-square material that we didn't finish talking about in class, and I figured I'd use this opportunity to just remind you about all of statistics. Keep in mind that every research question that we ask in statistics is coming back to this idea, this claim that there's something here, there's a connection, there's structure, there's ability or skill, that there's something to be observed. Well, whenever we make a claim like that, we want to be convinced, right? If I were to make the claim that I could juggle 25 eggs at one time, you probably wouldn't just take my word for it, right? You'd want me to convince you by demonstrating it. If I told you that I could read minds and predict whatever word you were going to think of, you wouldn't just take my word for it. You wouldn't be like, yeah, you seem like the kind of fellow who could read minds. You'd want me to demonstrate it. You'd want me to convince you. And our ideas behind that have always been the same. Anything that we observe in any experiment, any statistic that we take, we could always get those things by accident. We could always get them by random chance. And so our statistics, the whole tests that we do, the whole goal of this course is to find different ways to argue, hey, we don't think this happened by random chance. Is it possible that it could have happened by random chance? Yeah, absolutely, always. But if it's not likely, that's when we conclude that there's something significant. If I could guess the word that you were thinking of 9 times out of 10, out of all of the possible words that you could think of, that's pretty convincing. If I could juggle 25 eggs for, even just 3 seconds, I feel like that would be pretty convincing. I can't, by the way, if you're wondering. I don't know that there's gotta be somebody out there who can juggle 25 eggs, right? Looks like the world record for egg juggling is only like 5. That can't be true. Well, it doesn't matter. The whole idea of statistics is convince me that there's something here by arguing that it's not likely to have happened by accident, that it didn't happen by chance. And our model for doing so, again, always the same. We ask this question, if the null hypothesis is true, the null hypothesis being the one that says there's nothing here and everything you're seeing is by random chance. If that's true, then what are the chances that I would get what I got? In other words, what are the odds that I would get this by random chance? That's the big question that all of statistics comes down to. Hey, I saw a thing. What are the chances that I would get this by accident? If the chances are low, then we think there's something there. And if the chances are not low, then we're open to the possibility that there's nothing there. That's the whole idea of rejecting the null hypothesis and failing to reject the null hypothesis. So every statistical test that we have comes back to that question, leaving us with really kind of 2 big questions that we have to address in every new section that we look at. First of all, what would randomness look like here? What would random chance look like in this particular scenario? How could we model it? How could we simulate it? How could we recreate it? In the case of like Buzz and Doris, well, Buzz had a 50-50 chance of pushing the correct button. We said, hey, I know something else that's got a 50-50 chance, flipping a coin. I can use flipping a coin to model this scenario, and that would help me answer the question, what are the chances that Buzz would do this well by accident? And in every section, that's been one of our thoughts. How do I simulate randomness here? What does randomness look like? What does happening by accident look like? And how can I model that? How can I recreate it with something tangible that I can get my hands on? The second question that we've had to address over and over again is about the statistic. When I recreate this random chance, and when we simulate something 10,000 times to see what the world looks like when the null hypothesis is true, what am I looking for? What am I keeping track of? I want to compare what I saw to what would happen if the null hypothesis is true. But what am I keeping track of, right? What am I comparing in those 2 scenarios? Early on, that question was easy to answer. It was whatever it was that I'm actually looking for. Am I looking for The number of times that I was successful at doing something? Great, I'll keep track of the number of times I was successful at doing the thing. Am I looking for the proportion from a population? Cool, I'll keep track of the proportion, or the mean, or what have you. Once we got into Unit 2 and started looking at chapters 5, 6, and 7, that question became a little more interesting, because now I'm comparing two things. Is one thing bigger than another? Well, what am I keeping track of each time? Now I'm going to keep track of the difference between their proportions, or the difference of their means. And now that we're in our last unit, and we're looking at comparing multiple groups and their proportions, we had to answer that same question. First of all, what does randomness look like? And then second, what should I keep track of every time when I simulate that randomness? The first time we did this, the statistic that we used was the mean group difference, where I looked at all of the different comparisons between the two groups, the four groups that I had in this case, freshman, sophomore, junior, senior. I looked at the differences in all their proportions, took the absolute value of those differences, and then took the average of all of those absolute values of differences. That was the statistic we went with. Our idea of randomness here was, if the null hypothesis is true, then it doesn't matter what group you're in, so we can shuffle all the data around and put it in different groups, and then look at the mean group difference 10,000 times, and then we can see how likely is it that I would get a mean group difference of such and such a thing. You do this statistic, you find this statistic in each of those cases after you shuffle everything around over and over again, and then we can look at the results. We've got the applets for it, and we can check and see how likely is it that I would get this particular statistic. Well, now I'm making the claim that so why not just keeping the mean... Let's try that again. So why not just keep using the mean group difference? That seems like it works just fine. Well, there's a little bit of a downside to using the mean group difference when it comes to a theoretical approach, which is how a lot of statistics is done. Usually, when we're taking a theoretical approach, our line of reasoning is this. We'd like to know what this distribution is going to look like if we were to simulate. We've been able to simulate a lot of the times, but sometimes we can't. Sometimes simulation doesn't make sense in a particular scenario. Once you get to different statistical tests and maybe even some higher level courses. But we want to be able to come up with, what is this figure going to look like if I could simulate? Now, up until now, that hasn't been a big problem for us because it's almost always been a normal curve, especially if your sample size is a decent size. Well, the more you've got in your sample, the more your sample looks like the original population, which means it's harder and harder to get something that's different from the actual parameter of the population. Whether you're looking at proportion or mean or what have you, you're gonna most likely, more times than not, get the true mean of the population or something very close to it, and it becomes more and more rare to get something far away from it. Well, that means if we simulate enough times, like 10,000 times, I can expect this to look like a normal curve, and I can know kind of what that curve should look like. Here, when you check this box to overlay a normal distribution, it looks at, well, if I were to create the function, if I were to find the actual rule of the normal distribution that has the mean that I think this should have and the standard deviation that I think it should have, what would it look like? And it's pretty close, right? It's like really, really close. It's a really good fit. And we like that. That means that even if I didn't have the bars in the background, I could still draw all my conclusions by just having this curve. As long as I know what the mean and standard deviation is of this theoretical distribution, I can find standardized statistics. I can find confidence intervals. I can do all of the math that we've been able to do without ever having to do a simulation. But once you go to the mean group difference, it changes a little bit, and it becomes a little harder to use. Here I'm going to shuffle some options and do it another 10,000 times on whatever this data is. And, well, first of all, this isn't normal. But not only is it not normal, it's actually kind of hard to predict. it becomes a little more challenging to come up with a distribution that's going to model this sort of behavior that I get from keeping track of the mean group difference over and over again. And that's why we're looking for another statistic, a better statistic, that would allow me to better model what this is going to look like, to give me some sort of a formula or a function that I can use to predict what the mean and standard deviation would look like of this business after the simulation has occurred. So in class, I'd started sharing this example with you, where I wanted to look at people's ability to complete a task and whether that was influenced by the music that was playing in the background. We looked at the proportions of people that were successful when rock music, classical music, or no music was playing in the background. Now, the null hypothesis here is that there's really only one true proportion, the proportion of people who succeeded. In the null hypothesis for any multiple groups here, especially when we're comparing proportions, we're only interested in this column, the total people. According to the null hypothesis, this is the only column that matters. None of this means anything. It's all worthless. Because the null hypothesis says there's no connection, there's no structure, anything that we see, any differences that we get between these is just random chance. Truthfully, some people can do the task and some people can't. And the fact that they were in different categories as it happened, irrelevant, and random chance for any differences that we saw. There's only one real proportion here. Out of the 350 people who did this, 200 were successful. That's what my null hypothesis says is the only thing that matters. Now, we want to test that, right? The big questions in statistics: what does randomness look like? And what statistics should I keep track of? Well, we've already talked about what randomness would look like. It would look like taking all of the people who were who recorded in this table and shuffling them up into different groups and comparing them again. But what statistics should I use? When I keep track of this and do this 10,000 times and mix them up into different groups, what should I be writing down? And now we've got this new statistic that we're introducing called the chi-square statistic. The chi-square statistic, written using the Greek letter chi, which looks like an X, but curvier and more dramatic. The idea here, and there's two ways to calculate it. The first way that we calculate it is to look at all of our group proportions and compare them to this overall proportion of success, the one true proportion. The null hypothesis says that 200 over 350, that's the only thing that matters. It's the only thing that's real, the one true proportion. So we're going to examine that and test that claim by saying, great, we'll mix up all the groups and we'll see how far is each group proportion from this one true proportion. If they're all pretty close to the one true proportion, then it's very believable that there is only one true proportion. But if they're pretty far away from it, then it becomes a lot less believable. Now we want to standardize those numbers with a standard error. Standardizing is common because it gives us an ability to talk about the numbers more generally and have ideas of what sort of claims I can draw based on the values that I get. It also, it really makes our numbers a lot more meaningful because when standardizing is essentially accounting for the differences in standard deviations that I get. If my groups are very small, then it might not be difficult for them to differ from the one true proportion. And I want to be able to account for that. I want to make sure that groups aren't totally trashing the values that I'm getting on this just because they happen to be pretty small. The standard error that we're going to use to standardize them is this one, this square root of p hat times 1 minus p hat all over n sub I. The p hat is the one true proportion that the null hypothesis is claiming, and the n sub I is the size of each group, the sample size of each group that we have. From there, we still need to deal with negatives, and instead of taking absolute value, we're going to square them before we add them together. Squaring them works nice here for a lot of reasons. One is that it allows us to use calculus to figure out the specifics of this curve, but it also kind of makes bigger differences feel bigger and smaller differences feel smaller. so it highlights change better. Here's what that looks like with our table. From our rock group here, we've got 60 out of 100 is our P1, 75 out of 160 is our P2, and 65 out of 90 is our P3. I'll convert each of these to decimals to make them easier to work with, including my P hat, the one true proportion. Now the goal of my chi-square statistic is to first and foremost compare each individual group proportion with the one true proportion that the null hypothesis claims must exist. How far away are my proportions from that? So that's what we're going to do. I'll also need this 1 minus p because of that standard error that I just showed you. We take them on one at a time. For P1, I had 0.6. I compare that to the one true proportion. I find that difference, and then I standardize it by dividing by that standard error. Each standard error is going to look very similar, but I'll have p hat times 1 minus p hat divided by the number of things that are in that group, the sample size of that group. Going back to our table for a moment, you can see I had 100 that were here in the rock group, so my N1 is 100, N2 will be 160, and 3 will be 90. So I'll do this for all of the groups. I'll have 100 down here and 0.6 up here for P1. That gives me about 0.5780. I'll do it again for P2, now comparing my 0.4688 to the one true proportion and dividing by the number of things that were in that group. That gives me about negative 2.6225. And then for my third group, I'll compare that proportion to the one true proportion, this time dividing by 90 in my standard error, the number of things in my third group. And that gives me about 2.8909. These three values are giving me those standardized differences between each proportion and the one true proportion. Now to get rid of negatives and to highlight bigger differences, we'll square each term. And I totally forgot to erase this line, but I did write it twice in my PowerPoint. The formula's so nice, you write it twice. This works out to be about 15.578. The idea from statistics here is statistics as always. I'm simulating the null hypothesis 10,000 times. Each time, I'm looking at the chi-square statistic and saying, how many times do I get something at least this big? Not often, apparently. I only got it 6 out of 10,000 times. That means I can reject my null hypothesis, there's no difference between my groups, and conclude that there must be at least two groups that seem to be different from each other. And it's kind of a blanket statement, so I can't immediately conclude that they're all different from each other. Just because things aren't all the same doesn't mean that they're all different. Kind of like in our classroom. You don't all have the same age, but you don't all have different ages either. For that, we can look at our 95% confidence intervals, and look for the ones that contain 0 and the ones that don't. Here looking at the 95% confidence interval just for Group A and Group B, remember that's rock and classical music for me, that confidence interval doesn't contain 0. This is the confidence interval for the true difference of proportions in just those two groups. So this one, I suspect that these two groups are different from each other. The applet is very kind. It puts little stars next to the one that don't contain 0. Now this is one way to calculate our chi-square statistic, but there's another way to do it too. And they ultimately give you the same thing when you're in the similar scenarios. The one we just looked at is the way that you would calculate it when your response variable has only two options, like ours just did, success and failure, yes or no, up or down, dog or cat. As long as there's only two, you can totally use what we just did, because generally in that case there's one that you're considering better than the other, or one that you're focusing on, so it makes sense to talk about proportion there. But if you're working with a table where your response variable has more than two things, then this is probably the better way to go. Our alternate formula here does things a little bit differently. Before we could talk about the proportion of each group, but if my response variable has more than two things in it, that question doesn't really make sense. if I've got yes, no, and maybe, or cat, dog, and bird, right? What am I looking at, right? Is cat better than dog and bird, right? What would proportion mean there? Instead, we're going to take this tactic. Rather than compare proportions between groups, which doesn't make sense anymore, I'm going to compare the value that I get in my table to the value that I would expect to get in my table if the null hypothesis were true. Here's what we mean by that. Here's a different scenario that I'll let you just imagine what happened in the background here. I guess we interviewed a bunch of people who played sports and asked them what state they want to live in. So in this case, we had 50 people who played basketball who were like, yeah, Alaska, that's the place for me. I already play a winter sport. And the same goes for all of the rest of these. Now here's the key idea of taking this approach. If the null hypothesis were true, then everyone in each group would be distributed the same as the whole population. You look at this 100 people in my basketball group. Right now, 50% of them are in the Alaska category, but that's not the case for the whole population. I don't have 50% of my total 600 people in the Alaska category. I've only got 250 out of 600 in that category. The null hypothesis says that since out of the total population, 41.67% put themselves in the Alaska category, then if the null hypothesis were true, exactly down to the smallest detail, then in my basketball category, 41.67% of my participants would put themselves in this category as well. Here, 50% of them are in this category, but if the null hypothesis were true, 41.67% of them would be in this category. So I can figure out what should be in this cell, the expected count for this cell, by taking this number and multiplying it by this percent. Keep in mind, as a decimal, this is 0.4167. So you could think of this as a general formula is like this number times this number divided by this number. That's going to give me the amount of people that should be in this cell if the null hypothesis were true and everybody in the basketball category was distributed the same as the actual population. Same thing goes for California. Right now, 20% of this 100 is in the California category. But if the null hypothesis were true, it should be 35%. So I'll take 35% of 100, and 23.33% of 100. That's the expected count for those cells. And I can do this for the whole table. Now in this column, the 200 people in the baseball category, if the null hypothesis were true, they'd be distributed the same way as the full population. That would be 41.67% of the 200 should be here, 35% here, and 23.33% here. Same goes for the 300 people that were in the football category. I can do this for all 9 of my values. This gives me the expected counts of the whole table, the values that should be in those cells if the null hypothesis were true. Great, now what? Well, here's what happens. The next thing that we're going to do is take the values that were actually in the table and compare them to the values that I get from these expected counts. We're going to standardize these values. We're going to look at the difference between the actual values in the table and the expected count values, and then we're going to standardize them by first squaring our difference, and then they get divided by the expected count. I want to highlight here that this is kind of nice because instead of dividing by this awful standard error formula, we're just dividing by this number again. Let me show you what I mean. Here for our basketball, I think my animations are like really weird here. Yeah, okay, forget that. Here we go. In the basketball column, for example, originally my table had a 50 right here. We found that the expected count was 41.67. This does not need to be an integer. So what I'll do is first look at the difference between those values. What's the difference between the 50 that was actually there and the 41.67 that would be expected to be there if the null hypothesis were completely and 100% true? I'll look at that difference, square it to get rid of any negatives and highlight big differences, and then to standardize it, I'll divide by that 41.67 again. And I do this for all my values. For California, I'll be doing 20 minus the 35, squaring it, and then dividing by that 35. 30 minus 23.33, square it, and then divide by that 23.33. I'll get these values for all of the entries in my table. Here's what it would look like. So these are the values that we get from each of those terms, right? When I look at the differences, square them, and divide by that expected count, these are the 9 values I get. And now to find my chi-squared statistic, I just add them all up. They've already had the squares taken care of, so I just add them all up, and here I get 15.667. It's kind of a neat thing, by the way, if you were to remove this row, and if you were to do this process when you do have a response variable that has only 2 things in it, if you were to do this method of finding chi-squared or the other method of finding chi-squared that we looked at earlier, you should get the same value both times. This 15.667, that is our chi-square statistic. And from here, it's the same as ever before. I can run it 10,000 times. That's not what I thought was coming. I can run it 10,000 times and then see out of those 10,000 times, how many times did I get a chi-square statistic of at least 15.667. Gotta try it with a buddy here. Chances are you don't have a buddy near you who is taking statistics. So I guess think of it as try it on your own. Here's a chi-square statistic. I want you to find the chi-square statistic by hand and then use the applet to see if it's statistically significant. Go ahead and pause the video here and see if you can work it out on your own. When you work it out, you should get a chi-square statistic of about 8.59-ish. I made my table in Excel just to make it easier on me, but this is ultimately what it would look like. Here's the original table. These are the expected counts that you would get for each of those 9 cells. And sorry, I didn't change my labels for some reason down here. They should all be breath, peanut butter, and fish. These are the expected counts that you would get for those, and so these are each of the individual chi-square pieces, and when you add all of these up, you should get 8.59. Running it through the applet, I get a p-value of about 7.59% or 0.0759, which is not quite strong evidence. We got moderate evidence. Keep in mind you'll want to change your statistic to the chi-squared statistic over here. I also want to highlight that if you check this box to overlay the chi-squared distribution, it shows you the curve that you would get from the actual theoretical function, the theoretical chi-squared distribution, just like we could get a theoretical normal distribution from before. That will allow the applet to then show you the theoretical p-value that you would get if you hadn't done a simulation, which here is very, very close and very similar, of about 0.0721. I hope that this all made sense. Please feel free to reach out to me if you have any questions. Have a very wonderful Thanksgiving break, and I will see you when we all return on Monday. Take care.